Hello everybody, welcome back to the course Basics of Mechanical Engineering 3. We are discussing thermal science in the first half of this course. We have discussed about the vapor power cycle, gas power cycles in the recent lectures. I will take a tutorial session on the cycles, and this lecture is focused on power cycles. Directly I come to the revision or the recalling of the concept of the power cycles. For example, Otto power cycle was discussed. To recall, it is an idealized thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. It is the thermodynamic cycle most commonly found in automobile engines. Otto cycle consists of 4 processes: compression, heat addition, expansion and heat rejection. Compression is shown here from 1 to 2, that is isentropic process. In the PV diagram, it is shown here from 1 to 2, where the volume is decreasing and the pressure is rising. And in the temperature entropy diagram, 1 to 2 is here, where the temperature is increasing. Because compression is happening, the temperature increases and the entropy remains constant. Heat addition, that is a constant volume process. From 2 to 3, here the volume is constant in PV diagram, but the pressure is increasing. So, this is addition of heat which is being transformed to pressure. Now, in the temperature entropy diagram, from 2 to 3, the entropy rises and the temperature also rises. Then comes expansion, that is from 3 to 4, which is also isentropic. When I say isentropic, this means the entropy is constant, where the entropy is constant from 3 to 4, but the pressure is decreasing and the volume is also decreasing. And in the temperature entropy diagram, it is isentropic, the entropy remains constant and the temperature decreases because it is expansion. It is directly opposite to what a compression is. Heat rejection, which is opposite to heat addition, that is from 4 to 1, that is a constant volume process. Once again, when the volume remains constant from 4 to 1, the pressure decreases and the entropy and the temperature both decrease. Now, let us look at the relations so that we try to come to the numerical problems. In Otto power cycles, there are certain relations. When we talk about relations should be between pressure, temperature, volume. So, these are all relations where we have constant volume, constant pressure, constant temperature. It could be adiabatic or reversible systems. What are the relations? Let us see. Relations between pressure, temperature, volume in power cycles during isentropic process, isothermal process, isochoric process, isobaric process are given here. In isentropic process, that is we have adiabatic and reversible systems both here. It is T2 by T1 which is equal to V1 by V2 power gamma minus 1, where gamma is adiabatic index, and this is equal to P2 by P1 power gamma minus 1 by gamma. Gamma is adiabatic index because adiabatic process is involved here. So, adiabatic index will come into play. Then comes isothermal process, which is a constant temperature. Isothermal means constant temperature, in which P1 V1 is equal to P2 V2. This we have also discussed in the previous lectures, in the previous tutorials as well. Isochoric was also discussed, where constant volume is there, where P1 by T1 is equal to P2 by T2, or in other way we can say P1 by P2 is equal to T1 by T2. And isobaric, when the pressure is constant, the temperature and the volume vary, in which V1 by T1 is equal to V2 by T2, or we can say T2 by T1 is equal to V2 by V1. These are certain relations. These relations can be used to derive the efficiency of an Otto cycle. Now, in an Otto cycle, it is assumed isentropic, that is no entropy change, for which an ideal gas gives the relation T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1, that is equal to a almost constant. Using the compression ratio, that is R, which is equal to V1 by V2, and if we substitute here in this equation, we get T2 by T1 is equal to R power gamma minus 1. This gives me a relation where I can put my Otto cycle efficiency, that is efficiency of Otto cycle, as 1 minus 1 by R power gamma minus 1. That is efficiency of an Otto cycle. With this directly I will come to a problem statement in which we have been given the engine working on Otto cycle has a volume of 0.45 meter cube, pressure 1 bar and temperature 30 degrees at the beginning of the compression. This is an important point, at the beginning of compression. At the end of compression, the pressure is 11 bar and 210 kg of heat is added at constant volume. Determine pressure, temperature, volume at salient points. Now, what we have been given here is, we have P1 pressure as 1 bar, volume 1, that is V1 as 0.45 meter cube. Temperature, that is T1, is given as 30 degrees centigrade, which I could add directly with 273 to make it as 303 degree Kelvin. P2, the pressure at the second level is also given, that is 11 bar. And it has been given that heat added at constant volume is 210 kilojoules. That is Qs is equal to 210 kilojoules. So, this is a process where we have the compression, they say, and expansion would also happen. So, first cycle they say is the compression cycle, in which the pressure varies from 1 bar to 11 bar. I am just putting some values here. So, this is here like this. So, here I can put this figure in a way, from this pressure to the higher pressure at the TDC level, and we have a BDC level, that is at the top dead center and the bottom dead center. We have these points here which are mentioned, and from the bottom dead center I start my point 1. This is point 1. From here the compression happens from 1 to 2, compression happens. From here it stays at a TDC, because I am drawing, you would have identified it is a PV diagram, pressure versus volume. So, here from 1 to 2 compression happens, then at a constant volume we have heat addition. Because of heat addition, from 2 to 3 is addition of heat, Qs. Here also again we have from 3 to 4, that is expansion that happens. In the expansion the volume will increase, but the pressure is decreasing. This is 3 to 4, and 4 to 1 the heat rejection is there. So, it is QR, heat rejection. So, I will put it here like this. This is our compression, and here I have this side expansion, and this Qs value is also given as 210 kilojoules. Now, we need to determine pressure, temperature, volume at salient points. To find that, let us first consider the isentropic compression, that is from 1 to 2 process. isentropic when entropy is same, but we have variation in the pressure and volume. Here I will say process 1 to 2. The process 1 to 2 is isentropic compression. And for an isentropic compression, we recall the relation. We have the temperature pressure ratio here, T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. So, I can put this relation here. Here I get, or I put here T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. From this, I can calculate the value of T2, because T1 is given, P1 is given, P2 is given. T2 is to be calculated. So, here I have T2 to be determined. So, T2 from this relation turns out to be T1 into P2 by P1 power gamma minus 1 by gamma. If I put the values here, so though the value of gamma is not given here, if not given, it is generally assumed gamma is equal to 1.4. So, at gamma is equal to 1.4, I will put the value of gamma here as 1.4. So, this gives me T1 is 303 Kelvin, P2 is 11 bar, P1 is 1 bar, the power gamma minus 1 by gamma, that is 1.4 minus 1 by 1.4. This, to do the calculation, turns out to be 11 power 0.285, and I get the value of T2 as 601.15 Kelvin. T2 is gotten, and I need to now find the volume V2, because V1 is given. So, T2 is now here calculated. T2 is equal to 601.15 Kelvin. These are all calculated values T2. Now, I need to find the value of V2. To find V2, let me use the relation once again. T2 by T1 is equal to V1 by V2 power gamma minus 1. I will put this relation here. When I say V2 is to be found, I will use the isentropic compression temperature volume relation, that is T2 by T1 is equal to V1 by V2 power gamma minus 1. This gives me V1 by V2 is equal to T2 by T1 to the power 1 by gamma minus 1. So, I get V2 as V1 into T1 by T2, the power 1 by gamma minus 1. So, this gives me the value, if I put the value of V1, that is 0.45, T1 by T2, T1 is 303 Kelvin, that is given, T2 is calculated already, 601.15 Kelvin, and 1 by gamma minus 1, that is 1 by 1.4 minus 1. This gives me the value of V2 as 0.081 meter cube. So, this is process 1 to 2, that is isentropic compression. Now, next is process 2 to 3 at a constant volume process. I will put it here as process 2 to 3, that is constant volume process. Here, to recall, at a constant volume process, we can have this relation, that is P2 by P1 is equal to V1 by V2 to the power gamma, or vice versa. I can say P1 by P2 is equal to V2 by V1 to the power gamma. So, if volume, pressure, temperature, everything if I put as C, that is, I say if volume is equal to C, pressure is equal to C, and temperature is equal to C, that is general gas equation, we say P1 V1 by T1 is equal to P2 V2 by T2. This is a general gas equation, and this general gas equation you have studied everywhere in your syllabi, in your senior secondary, in your pre-engineering studies, but we are now trying to talk about engineering processes, that is constant volume processes, when we have the adiabatic index also that comes into the play. So, here we will have a further extension of this, or we can even say if this process I can even put it in this way, that is P1 V1 is equal to MR T1, that is a perfect gas equation. So, here from 2 to 3 I am talking about the state, stage 2 to stage 3. So, it is, I will call it stage, or it is state even. This is initial state, two, and final state is 3. Here I can put it in this way, P2 V2 by T2 is equal to P3 V3 by T3, and we are talking about a constant volume process. That means at 2 point and 3 point at both the states the volume is constant, which means V2 is equal to V3. So, I will cancel these variables here because V2 is equal to V3. So, now we use, here is the heat addition now as well. There is QS, that is QS here 210 kilojoules. So, I will say using QS, that is 210 kilojoules of heat that is added, we have the relation mCV into T2 minus T1. Here in this case it is 3 minus T2. This is equal to 210 kilojoules. And using the perfect gas equation, while putting the values P1 V1, this relation here is equal to MR T1, I can find the value of M, that is M is equal to P1 V1 by RT1. This is equal to, what is P1? 1 bar pressure, it is 1 into 10 raised to the power 5. What is V1? 0.45 meter cube, and R is 287. and T1 is 303, that was 30 degrees centigrade, 303 Kelvin. I get the value of M as 0.517 kg. This is the mass that we have gotten here. Now, putting this value of M in the above relation, here I get MCV, that is 0.517 into CV. CV is the specific heat at constant volume process, that is 0.718 into T3 minus T2. T3 is to be determined because I am trying to find T3 here, minus T2. T2 was calculated here, that is 601.15, and this is equal to 210 kilojoules. This whole calculation would give me the value of T3, that is temperature at the third state, as 1167 Kelvin approximately. Now T3 has been gotten. I'll put the value of T3 here. Okay, V2 was also calculated. I'll put the value of V2. What is V2? V2 is 0.081 meter cube. Right. Next is, I have gotten the value of T3. T3 is 1167 Kelvin. Now, using this, I can also find the value of P3. Now, which relation could I use? To find the value of P3, pressure at state 3, and this is a constant volume process where the pressure is increasing. So, at point 3, what is the pressure? It should be anyway more than 11 bar. So, I am trying to find pressure here. What is the pressure at this point? So, this pressure could be taken from the general gas equation. I will try to put this equation here for the state 2 and 3, that is P2 V2 by T2 is equal to P3 V3 by T2, and we know V2 is equal to V3. Therefore, the same thing is coming here. I get P2 by T2 as P3 by T3. This is T3 here. In a way, I get P3 as P2 into T3 by T2. I'll put all the values. P2, pressure that we calculated is 11 bar. Temperature 3 is 1167 Kelvin. Temperature 2, T2 is 601.15 Kelvin. This gives me the value of P3 as 21.34 bar. So, here P3 is 21.34 bar. So, this is 21.34, right. So, we have been given the volume, initial volume 1 as 0.45 meter cube, that is V1 is equal to V4 is equal to this value, and we have calculated the value of V2, that is 0.081 meter cube. This is V2 is equal to V3. Now let us come to stage 4. We need to find the value of the pressure and temperature at the point 4 or state 4. Though V4 is same as V1, that is 0.45 meter cube, we need to determine the value of P4 and T4, the pressure and temperature here. So for this, let me now again try to see an isentropic expansion process, that is process 3 to 4. This is isentropic expansion now. Here, just to recall, we have two ratios. One is compression ratio and we have expansion ratio. Compression ratio is RC, that is V1 by V2, and expansion ratio is RE, that is R expansion. This is equal to V4 by V3. Now we can put it in this way: P4 by P3 is equal to V3 by V4 per gamma, or this is equal to, because V3 is equal to V2 and V4 is equal to V1, and put it in a way, this is V2 by V1 per gamma. So this gives me the relation of P4 as P3 into V2 by V1 per gamma, and P4 then turns out to be, putting the values here, of P3 as 21.34 bar, V2 is 0.081 meter cube, V1 is 0.45 meter cube to the power gamma. Gamma is 1.4. This gives me the value of P4 as 1.93 bar. So P4 is 1.93 bar. That means P4 is down here, somewhere down here, that is 1.93 bar. So this curve might not have turned perfect, but the values are in the same order. 1 bar is at state 1, at state 2 it is 11 bar, at state 3 is 21.34 bar, and at state 4 the pressure is 1.93 bar. This is pressure in bar and volume is in meter cube. Now we have gotten everything. Now I can just calculate the value of T4 using the relation once again. T4 by T3 is equal to V3 by V4 to the power gamma minus 1. This is again equal to V2 by V1 per gamma minus 1. Therefore, T4 is equal to T3 times the ratio of V2 by V1 to the power gamma minus 1. This gives me the value of T4 while putting the value of T3 as 1167 into 0.081 by 0.45 to the power 1.4 minus 1. This gives me the value of T4 as 587 Kelvin approx. So T4 is 587. So this was an important problem statement though it was little lengthy or long problem statement, but at all the 4 stages, what are those credentials, what is temperature, what is pressure, what is volume at all the salient points, that is point 1, 2, 3 and 4, these were determined for the Otto power cycle. So, let me take a smaller problem on the Otto power cycle. An ideal air standard Otto cycle has a compression ratio of 9. The air at the beginning of the compression is at 100 kilopascal and 300 Kelvin. At the beginning 100 kilopascal and 300 Kelvin. The maximum temperature in the cycle is 2100 Kelvin. Assume air behaves an ideal gas with constant, that is CV, that is specific heat at constant volume process, as 0.718 kilojoules per kg Kelvin. This is a standard value. If not given, this is taken as 0.718 kilojoules per kg Kelvin. In the previous problem as well, I have taken the value of CV in the same fashion. Here also I have taken the value of CV as 0.718 kilojoules per kilogram Kelvin, and this is used in the calculations here. You can see here I have put the value of CV. This is CV. Now, gamma is also given here 1.4. We need to determine the thermal efficiency of the cycle and work output per kg of air. So, this is a similar Otto power cycle. I will draw this time the temperature entropy relation. Temperature entropy relation, because it has been given compression ratio is 9. So, I will put value of R given here as is 9. P1 is 100 kilopascal. Temperature 1 is 300 Kelvin. So, at some point the temperature is 300 Kelvin and maximum temperature T maximum. So, if I need to draw, I will call it as T3. This is 2100 Kelvin. So, here T1 is 300 Kelvin. We will put temperature in Kelvin and we have somewhere 2100 Kelvin, and we have been given CV and gamma. Now, here at 300 Kelvin entropy would change. This is stage 1, where at 300 Kelvin entropy is at this level, and at 2100 Kelvin we will put it somewhere here. We have a constant entropy, and if I draw this, this is from 1 to 2, the entropy does not change, and when heat input is here, the entropy increases, and this becomes my temperature 3. This is stage 1, stage 2, stage 3. I call it stage or state. So, then I come down to stage 4, and then again heat goes out. So, here I have Q in, here it is Q out, and this I can call it as 2100 Kelvin as my temperature T3. Thermal efficiency of the cycle, first part. To find the thermal efficiency, we have seen it in the relation. Thermal efficiency is given by 1 minus 1 by R power gamma minus 1. So, I will call it thermal, that is efficiency thermal. This is equal to 1 minus 1 by R power gamma minus 1. I have been given the values here. Compression ratio value is also given, 9 value it is given here. So, I will put those values, 1 minus 1 by 9 power 1.4 minus 1. This gives me the thermal efficiency as 0.58, which means 58% efficient cycle. Right? First part is over. Now, second part is work output per kg of air. Second part, that is work output. For that, let me see process 1 to 2, where T2 by T1 is equal to R par gamma minus 1, which means T2 is equal to T1 times R power gamma minus 1. This is equal to value of T1 is 300 Kelvin, value of R is 9, gamma is 1.4. I'll put the values. 300 into 9 power 1.4 minus 1. This gives me the value of T2 as 722.4 Kelvin. Now, for the process 3 to 4, though I have determined the temperature 2, that is T2 here, as 722.4. So, these are calculated values. I have determined T2 as 722.4 Kelvin. So, I need to determine T4 now. To determine T4, the process 3 to 4 is here. In the process 3 to 4, again same relation, T4 by T3 is equal to 1 by R par gamma minus 1. You see this relation here, we are using the same. This gives me T4 is equal to T3 into 1 by R par gamma minus 1. This is equal to, I put the value of T3 as 2100 Kelvin and put the value of R and gamma. And calculated the value of T4 as 872 Kelvin. So, T4 here is 872. It would be somewhere here. This is T2, this is T4. I will put the T4 value here as 872 Kelvin. But the question is work output per kg of air. To find that, I'll continue this here and put Q in, that is equal to CV, which is specific heat at constant volume, into T3 minus T2. This is equal to 0.718 into 2100 minus 722.4, and Q in is 989.1 kilojoules per kg. Then comes the final calculation, that is the work output per kg of air. Work output is efficiency times the input heat per kg, that is eta into Q in. This is equal to 0.58 into 989.1. This is equal to 573.67 kilojoules per kg. I'll put it here. Work net is equal to 573.67 kilojoules per kg. So, with this the Otto power cycle is completed. I will come to the second part of the power cycles in the second part of this tutorial, where I will discuss the diesel cycle. Thank you.